Hi folks, welcome to this new tutorial about ratios and how they're useful in geometallurgy and in Cancha, the geometallurgical software. So I'm going to talk about why ratios are useful. Ratios in geometallurgy are not just mere numbers, they're whispers of patterns and echoes of relationships, and they're silent narrators of the underlying truth. So I'm going to talk now, first of all, why ratios are so useful in predicting geometallurgy. Where are ratios used in geometallurgy? First of all, they're fundamental for the automated mineralogy. So anything like QuimScan, basically the instrument's looking at the ratios between the elements and determining what the mineral identity is based on its elemental constitution. So we're already using it in that sort of context. It's also used extensively in acid-base accounting. So if you want to predict whether a waste or tailings is going to be potentially acid generating, you're looking at the ratio of acid production versus acid consumption. Geologists use it all over the place in lithology identification, looking at ratios of rock-forming elements such as aluminium, potassium, sodium, whatnot. And optics, so you look at things like, for example, the gold to sulfur ratio in a refractory gold project. If you don't have enough gold, you can't pay to oxidize the sulfur. The old rule of thumb was 1 gram of gold per 1% sulfur. I think that still holds fairly close. But basically, you're looking at the ratio of the gold to the sulfur, basically the ratio of your benefit to costs. And in concentrate qualities, so people might look to see what the ratio of copper to arsenic is, or zinc to fluoride, all kinds of different things that might be in the concentrate that might give it a better or worse concentrate quality. And in process development, we use it all the time for flotation projects. We might be polymetallic, we might be looking at the copper to sulfur ratio, or the zinc to lead ratio, or the copper to zinc ratios, nickel to magnesium, stuff like that. There's all kinds of ones where you'll actually choose a different process if you've got different ratios of things in the ore. So why are they useful? Well, first of all, they give everything in a standardized way. It's really independent of the going to be constant record. Depending on doesn't really depend on the value that's high or small. It can give you something constant throughout the whole block model, throughout the whole deposit. So it's by having a constant value, it makes it easy to be able to know where you're at. It can simplify complex data. So if you're just looking at a whole bunch of different numbers, it's difficult to really understand what you're looking at. It's hard to tell if there's outliers or whatnot. But if you've got everything reduced down to a single ratio, then you can see on a single one-dimensional space, you can see how things are. It's a universal language. So, some people might talk in grams per ton, others in ppm, milligrams per liter versus, I don't know, whatever else. But basically, at the end of the day, regardless of units of measure, you're able to bring everything back to a ratio, and it's something that everybody can understand, through geology, mining, and metallurgy. So it converts concepts that might be abstract, that might be difficult to understand. Looking at ifs and thens. If copper's high and zinc's high, then this is fine. But if this is high and this is low, then there's another thing. Yeah, that's kind of complex language. But if you can just say, oh, look at the copper to zinc ratio, and look for that one number, and if it's greater than or equal to that number, then you've got one set. So it's a good way to everybody get behind an idea. So more than that, the ratios are also super useful because they, like I said, they show the underlying truth. Okay, so a great example of that would be the body mass index, BMI, that we use to check our health. And basically, you could have a weight you could be perfectly healthy with a weight of 75 kilos. And you could be perfectly healthy with a weight of 110 kilos. This is the same with the height. You could have somebody with a height of 150 55 centimeters, 185 centimeters. These are completely acceptable heights, normal, regular people. But if we apply the BMI, we might see that one person has, quite a lean body mass. These two might be on the border of obesity, and this one's morbidly obese. Okay, so you've got, by looking at the height alone, you can't really tell where you're at. And if you look at the weight alone, you can't really see where you're at. But you look at the ratio between them, create a new data that compares the two, and you've got a very clear number that can tell you where you're at. So that's a layman's example. Now let's get into some geometallurgical ones. So a common one that we might look at is a sulfur to iron ratio, where if pyrite oxidizes, then the sulfur will be washed away and the acid, and the iron will be left. So if you look at the sulfur to iron ratio, where there's an oxidation, you'll end up with high iron and low sulfur, therefore a small number. Copper to sulfur ratio. So this can help you understand where you're at in terms of copper, which you might be trying to recover, and sulfur, which would sort of represent copper sulfides, but also it could be pyrite, pyrrhotite, things like that. So it could tell you how dilute your copper is versus all the things that want to float in flotation. Silver to copper ratio, gold to copper ratio. This is going to give you an idea about what sort of acid consumption cyanide consumption you might have in a cyanidation. It might be able to see that what sort of mineralogy you might have as far as geological events, because there might be a different event that brings the silver. Epithermal, for example, might bring silver, whereas the copper might have been brought in a porphyry event. And so there's a sort of an example where if you look at the ratio of those two, you might be able to better identify what the geological event is that's controlling the geometallurgy, and therefore you're able to better predict it. Potassium to aluminium ratio or sodium to aluminium ratio. These are just a couple of examples of what you can look at to see the level of alteration. More altered rock might be weaker, it might be easier to grind, it also might have more clays, which might make it more difficult for flotation. So these rock forming elements, although they're not super useful a lot of the time in geometallurgy as far as predicting metal recovery goes, there are times where alterations can have a big impact. So these sort of ratios can be super useful. Iron plus calcium divided by magnesium gives you a better idea about what carbonates you're dealing with. Aluminium plus potassium divided by magnesium will tell you about the argillic alteration, and how much transition you've had from sericite versus chlorite. Iron plus calcium divided by sulfur gives you a better idea whether you get anhydrite versus pyrite. Calcium to magnesium will tell you about more calcite versus dolomite, which would have an effect on potentially solution chemistry. So concerns about the implementation, you got to be really careful because the ratio has to be useful at the block scale. When I'm in the block scale, I'm talking about the 10 by 10 by 10 block. So there's really no point in talking about ratios if they're really erratic on the meter by meter basis. Or for example, sometimes people go down the wormhole of saying, well, we've got pyrrhotite and pyrite, in the presence of specularite or something like that. So you've got a whole bunch of iron minerals, you've got different sulfur, things like that. So you might be looking at the ratio between iron and sulfur, but really it's not going to really tell you anything because you've got a whole bunch, you might have magnetite there and stuff like that. So you've got these iron oxide minerals, plus you've got iron sulfide minerals, and maybe you've got some copper sulfide minerals or some base metal sulfides. So if it's all over the place in that respect, it's not going to be useful if you do kriging at a 10 by 10 by 10 level. Okay, so whatever you're dealing with on the ratios, you've got to remember it's got to hold the relationship, and it's got to be a useful relationship when you go to the macro scale for geometallurgy. There's no point in understanding that you've got, sphalerite and marmotite in different areas of the mine. If you've got a bunch of pyrite and peritite there as well, you're never going to be able to use the iron to zinc ratio in order to determine what sphalerite species you've got. So you're going to have to find some other way to work out what your sphalerite zinc species is, other than just a straight up zinc to iron ratio. Okay. So some tips. First of all, ratios can become low values can be erratic and meaningless. So basically, if you've got a very low grade copper, looking at the acid soluble versus total copper ratio might not mean anything because you might be near the detection limit for copper. So really, you shouldn't be using ratios, and you shouldn't be looking at them where the analytical errors are going to be a strong component of the value. So you need to filter the ratios for minimum values before using them. Get rid of those values that are near detection limit on the denominator, or you could get in trouble. Division by 0 gives infinity, so yeah, just be careful with that. If you're trying to work out, which term's going to be the numerator and which one's going to be the denominator, try to make it so the term gets smaller at high values, and rather than getting massive at high values, because the way that data science works is that you might end up, losing the resolution there. If the scale goes up to 100 million and you're trying to sort out the difference between 24 and 25 on the scale, you're going to be in trouble. So better to flip it and do the inverse calculation and try to get it where the outlier numbers are going to give a logarithmic scale, sort of, an inverse scale difference rather than an exponential scale difference. So avoid those exponential scales. It's going to screw up, especially in Cancha and the software. Generally the focus is linear regressions and clustering. So by having these massive outliers, it's going to screw up all those sort of scales. And try several approaches. So, there's not one set of ratios you should be looking at for any particular commodity. You need to try them out and see which one works for you. Every project's different, and you have to just brainstorm and think about what elements you've got, what species you can measure and stuff like that. Work out where the trade-offs are, and then put that together in different ratios and see which one's most useful. Okay, so now I'm going to jump into an example here. It just uses Project Hope dataset, and how you're going to use ratios in Cancha. Well, first of all, you can come to derive features, and you can create here a ratio. For example, let's create a ratio of iron to sulfur. So let's just go iron divided by sulfur, and we'll call that E divided by S. And so now we're going to have this, you can see we get this new thing here, green color, and it's got values from about 0.2 up to about 1,000. Hit apply and reconsolidate that. And now if we go to logs, we can see, so here we've got a bunch of elements. Get rid of some of these. And let's put on here the iron. We'll put here on the sulfur. And now we're going to put on the iron to sulfur ratio. So you can see that we've got iron, as I was telling you before, you've got iron up here, which really, they've got a higher concentration of iron here, higher concentration of sulfur in the potassic zone. But you can see here that the iron is similar values all the way down. You've got no sulfur, but when we look at the iron to sulfur ratio, that's a much more dramatic and much more a cleaner way of finding out where that transition is. Okay. So let's also, we've got the sequential copper. So let's go here, right click on assays, and we'll add a ratio. We could also come here in features, and there's a button here for adding a ratio. We're going to add it to the assays table, and we're going to add acid soluble first, then cyanide soluble, then residual copper. So I'm double clicking and they're coming up here. We could also click on the arrows here and click on them like that and get them in and out. The order is important because this is the order they're going to be in. And as I mentioned in the other part of the tutorial, I said, you've got to be careful with low values. So what I'm going to do here is I'm going to put, don't use this ratio for anything less than 0.1% copper. Okay, so I'll just hit apply to that. I'm going to end up with this new ratio here as a new feature in assays. It says ratio acid soluble, cyanide soluble, and residual copper. So now we come back to logs. I can add this one to the chart, and as we can see, now we've got these ratios of the three. So let's find a better one. Okay, here's a good one here. So we can see here that in here we've got the cyanide soluble. Basically, we can see here this is where the supergene is, and then down here it's all red. This is where all the hypergene is, and you can see right here the transition between supergene and hypergene. Okay, let's just put the copper grade on there as well. We can see that the copper's been enriched here in the supergene zone. Okay, so now we've got this way of looking at this in a nice way in the logs. Something else we can do is we can right click on the ratio and we can say make index. Okay, so I'll just click on that and it's going to create indexes for these values here, right? So now if I put on here on the logs, I can put the acid soluble, cyanide soluble, and residual. Looking at these individually, you can sort of see here that they got the, sorry, this is, what did I not do? I didn't put the cyanide soluble on. Why not? Get it together. All right. So here we've got acid soluble, cyanide soluble, and residual. And you can see it ties in nicely with this. But we can also now have these indexes where this is a fraction of the total. And now we can see that here you could sort of see, because of the scale, you could say, oh, maybe there's a lot of acid soluble here. Well, not really, because here we can see that it's all predominantly cyanide soluble here. So using those indexes of the original values that went into the ratio, here we can see a much clearer story about what's going on. Okay, so now that's so now we've used these values to create a ratio. We've also created the index. Now, what other things we can do in Cancha? We can come here to the analysis area. We can come here, for example, to the ternary plot, and we can put on here the residual on the right, put the cyanide soluble on the left, and this acid soluble on the top. And now we can see where each of these drilling intercepts is on a ternary diagram. Down in this corner, it's essentially all the chalcocite, bornite, digenite, energite, things like that. That would be high cyanide soluble. In here, you can have some covellite, which is only sort of 70% cyanide soluble. Down here, it would be chalcoporite. And I guess if we put on a heat map, we can see better, where we've got some secondary here, we've got some primary, and here we've got some mixed stuff here. Now, this area here is what's usually referred to as refractory. It's where you've got very little cyanide soluble, but you've got oxides together with residual, acid soluble with residual. And that could be things like goethite, hematite, limatite, things like that, that won't float, but they, they're up at the top there. They're part of the oxidation product, but they're not acid soluble. Okay, and so we could even put on here, the iron to sulfur ratio, for example, as a color. And we can see here we've got high iron, low sulfur, and then down at the bottom, these are all sulfides where you've got high sulfur. Yeah, that sort of thing. So there's one use of ratios. Another use of ratios would be here, for example, where we might come to look at, well, let's use a different thing. Let's use the, I don't have Yeah, let's just put the acid soluble index, the cyanide soluble index, and the what's it called, the residual index. Reason it's not working. What we're doing, maybe come to the block model and look at the. Okay, let's do that. Let's come to the block model and look at the copper to gold ratio. Come on, what's going on? What am I using here? Oh, sorry. This is a stack plot, and you should only be using metallurgy data for the stack plot. What I should be using is the ratio chart. So how's that for a tutorial? Showing you wrong how to do it. So here we'll put the gold and we'll put the copper. And here we can see in the block model, we can see the ratio of gold to copper. Now, obviously, it says grams per ton versus percent, but you can see across the deposit, you've got some that have very high gold compared to the copper, but generally it's quite flat. This would be considered fairly constant. It's not a big variation there. Let's pull it off the gold and we'll put on the iron, and we can see here it's fairly constant in that respect as well. Maybe we should put on here, for example, we could put on the acid soluble, cyanide soluble, and residual. And here we can see how much of the deposit has got a certain proportion of oxide. So you say, very, very small proportion of the block model here has more than 20% acid soluble. About a third is supergene of the blocks, and about 2/3 is hypogene. So this is a pretty cool graph for interpreting this. You might put on, for example, arsenic and copper, or you might put on, copper, lead, zinc, for example, in a different project, and you'll be able to see the ratio very quickly. What it does is it's ordering the first thing you've got, which is in this case is acid soluble copper. This is ordered from low to high, and then the rest of the blocks are added on according to their ratios, and so you're able to get a good view of that. So those are the different ways that you can use ratios. I'm sure there's other ways we can look at ratios, but for the time being, I think that's a good enough overview. So any questions or comments, just add them in the comments to the video here, or email me directly. And thanks for your attention.